Okay, I will give you the example in a second. It is worked example number 8.
Spooky scary equations saying Sheridan.
Oh no, it's not example 8. Sorry, we did example 8. It is example 9. 6.9.
Oh, the circus performer.
Yeah, the circus performer. Come on, that's going to be fun, isn't it?
The one with displacement.
Just imagine it's Bob. Maybe this is how Bob met his demise.
Bob Senior, Bob Junior, Bob Junior Junior.
Okay, so the question says a circus performer rides a unicycle along a stretched tightrope. The tightrope is modeled as a straight horizontal line, and the velocity is modeled as. Okay, how do we read this? Okay, how we read this is these are 3 different equations depending on what time. So during the first 2 seconds, what can you tell me about the unicycle's velocity, Trev?
During
The first 2 seconds, so from.
first 2 seconds.
So there we go.
Velocity is 1.
Yeah. In other words, it is. What can you tell me about the velocity? It's
Constant.
constant, because it stays 1. That's the definition of constant velocity. It doesn't change. Okay. If you had to graph the velocity, what does it look like?
A straight line.
Yeah, straight horizontal line at 1. Right. For the next 2 seconds, so from 2 to 4 seconds, what could you tell me, Zara, about the velocity there? Yeah, it increases, eh? With what?
Acceleration.
What kind of
why is it
acceleration?
increasing?
And what kind of acceleration?
Constant.
Constant acceleration, because it's a linear function. What is the acceleration?
2 meters per second.
The gradient of that graph gives you the acceleration, yeah? Right, what can you tell me about its final couple of seconds?
Decelerating.
It's decelerating, okay? Is it decelerating in a linear fashion?
No.
No,
It
it's,
finishes at 49 seconds.
it's in some kind of decaying exponential. That red line with blue highlighted, that's his deceleration.
It's a very long time to stop, 49 seconds.
Okay, so the first part of the question says calculate t. So have a look in the equations there. Notice how they haven't given you the end deceleration yet, or the end time. They've given you a variable and they want you to go work out what it is. So how could you calculate what that should be?
You just substitute, because we only have one variable.
Well,
You just substitute t into the t, and then you just solve.
okay, well we want to find out what big T is. Big T is some time. There's an actual time.
It's
But
49 seconds.
I want you to, yeah, but how do we get there? It's the
Because
question.
when velocity is 0.
Well, that's what I'm getting to, right? What happens when the guy gets to the other end of the tightrope?
You stop.
He stops. And what is our velocity when you stop?
0.
So which one of those equations do I need to make equal to 0?
The last one.
The last one, because that's the one that happens to be in that part of the stage. Remember, this is a staged problem. Stage 1, stage 2, stage 3. So for this part of the problem, our velocity is what? 7 minus the square root of t. So I want to find out at what time he's going to stop. So what can I do to velocity? Velocity must be equal to 0, because that's when I'm going to stop. And now I just solve. 0 equals 7 minus square root t. How do I get rid of the square root? Yeah, square root. But then I have to? So 49. Simple as that. 49 seconds. So what's big T equal to? 49 seconds. So at what time does this unicycle come to stop?
49 seconds.
49 seconds. And these, remember, when you draw up these equations, you have to take into account the previous stages, right? So that is why this is what that graph looks like. So the purple line, can you see the purple line at the bottom?
Yeah.
Can you see how it's constant velocity? Then notice how we have a straight line graph, because it was constant acceleration. Constant acceleration creates linear velocity. And then we decelerated with some what would you call that? A
Parabolic function?
decaying something. The name eludes me now.
It done did a slowness.
It goes down very slowly. Okay?
decaying exponentially.
Now, if these graphs hadn't taken into account the previous velocities, they would have all been shifted up to the origin, and we wouldn't have a continuous flow. Notice how we go from yellow, green to blue. Okay. So this isn't 49 seconds in stage 3, this is 49 seconds total.
So you can technically calculate further.
Yes, well that's what you're supposed to be able to do. Okay, what does the next part of the question say? Calculate how far the performer cycles. Okay. Now, what do I have equations for?
Velocity.
I have velocity equal to 1 between 0 and 2. I have velocity equal to, yes,
Can I go to the bathroom?
very quickly, equal to 2t minus 3 between 2 and 4. And then velocity equal to 7 minus square root t between 4 and
49.
49. Where are my equal to signs? They are all over the place. Okay, so I need to calculate what? Displacement.
You're gonna have to do it 3 times, but
Yeah,
that's
I
fine.
have 3 velocity equations, so I'm going to have to. How do I get from velocity to displacement?
Isn't it VDT?
I need to integrate. I can't differentiate. If I differentiate velocity, what do I get? I get acceleration. I don't care about acceleration, I want displacement. So, how would we go about doing this?
You know time, so you just take.
Don't I know all the values for
Yeah,
t?
you just take your starting and ending values.
I'm just going to have lots of integrals.
Yeah.
Okay? What are my boundaries going to be?
The time.
All my times that I want to integrate from. So let's go. Displacement, right? Total displacement is going to be equal to what? Let's start with the first one. The integral of 1. What are my lower and upper boundaries going to be?
0 and 2.
0, 2. Right? Why do we not care for Charlie?
Because we have boundaries.
Yeah, technically we know that Charlie is 0. Yeah? Okay, we're going to add on the integral from this part of time. And what are my boundaries going to be here? 12?
4. No.
Think about where this equation
2
is
and
at.
4.
2 and 4. And we're going to add finally the integral of 7 minus square root t. Where are my boundaries
4
here?
and 49.
4 and 49. Okay, so nothing actually too complicated, we just have 3 sets of equations to integrate. So let's do them one at a time. Right, we have, what happens to 1 when we integrate it? It becomes,
1.
it's t to the power of 0, we raise the power by 1, so it becomes t to the power of 1 divided by 1, which is just t. Right, from 0 to 2.
So 2.
It's going to become 2, yeah? Plus, let's anti-differentiate that. We're going to raise the power by 1, it's going to become,
It's 5 minus 1.
so this is going to become
4.
t squared minus 3t.
5 minus 1.
No.
Oh, we're going to get there, we're going to get there. Remember, we're not jumping steps here, we're going to, this is our primitive function, we're going to do these step for step. Don't skip steps. These are marks here. Okay, let's anti-differentiate that. Now, can I anti-differentiate square root t? So here off to the side, I'm going to rewrite that as 7 minus,
1, t to the power 1
yeah? I can't anti-differentiate the square root, I need to change it into index notation first. Okay, let's, if I anti-differentiate 7, I get
70.
7t, and if I anti-differentiate that, what am I doing? I'm raising the power by 1, so it becomes 3 over 2. And then I'm dividing by the new power, which is 3 over 2. So it becomes 2 over 3 t to the power of 3 over 2. Between 4 and 49. So these problems just require a lot of work because now you've got 3 sets of primitives to find, right? So here we go. Number 1.
2.
T of 2, which is 2 minus 0. There's my first one. Second one. T to the power of, 4 to the power of 2 is 16 minus 3 times 4 minus 2. So what's t to the power of 2 to the power of 2?
4 minus 6.
4 minus 6. Okay. Use the brackets, please. Yeah, don't forget.
So it just becomes 6.
So here we will have, right? So that's going to be what? 16 minus 12, which is 4, minus 2, which is 6. So we'll have 2 plus 6. There we are. Right, final one. Might require a calculator. Times, which number do we start with first?
49.
49 times 49. What am I missing? Minus sign here. Minus 2 over 3 times 49 to the power of 3 over 2. Minus that thing when it's 4. Somebody just give me the answer.
It's 99 and 2/3 total. So
99 and 2/3.
the total of everything.
For everything.
It's 91.
Is this one 91?
91 and 2.
91. Sorry, I'm just running out of space. Okay. Don't forget that we would still have to take here 7 times 4 minus 2/3 4 to the power of 3 over 2. Okay? And because 749 is a perfect square, that's why you end up with a nice solution and not some decimal nonsense. Okay, so adding all these together, we get displacement equal to 2 plus 6 plus 91 and 2/3, which is 99 and 2/3
Meters.
meters.
And
So the only difference between this question and all the other questions is that sometimes the equations changed depending on the different times. Okay? Think about when you drive a car. You don't drive a car the same way constantly. Sometimes you are driving at constant acceleration. Then you have to overtake. Maybe you overtake with constant acceleration. But when you decelerate back to normal speed, perhaps that is not a linear.
and then your acceleration also depends on RPM and
Yeah. So I mean, but we could model equations for how your speed changed.
Yeah.
But it's not going to be the same. It's going to be
and
different.
it's going to be difficult.
Yeah. Well, if you have a computer plugged to your
True.
car, it could actually pop lots of equations out for you.